Imagine checking into the ER with a deadly 106-degree fever. A doctor who only offers to keep your temperature from climbing is missing the point. To survive, your body must actively cool back down to 98.6. Current global climate goals focus almost exclusively on slowing the rate of new emissions. This strategy aims for stabilization, but it contains no plan to address the heat already trapped within our atmosphere. This graph shows where we stand. Even if we transition to 100% renewable energy tomorrow, global carbon levels would level off at 420 parts per million. This is legacy carbon, a massive, stagnant stockpile of greenhouse gas that keeps the planet warming. Returning to safe, pre-industrial levels requires the removal of 1,000 gigatons of CO2. At $1,200 a ton, current direct air capture machines are too expensive. Clearing 1 trillion tons of legacy carbon using mechanical vacuums would cost more than the entire global GDP. Net zero is a vital first step, but it is not a destination. Leaving 1 trillion tons of carbon in the sky keeps the climate in a catastrophic state. Survival requires a strategy for active removal. The Earth's atmosphere has successfully scrubbed itself of carbon dozens of times throughout history. These cooling events happen naturally, long before the arrival of human technology. We have a physical record of these shifts. These tiny bubbles trapped deep within Antarctic ice cores are samples of ancient air. They show exactly how global CO2 levels plummeted during previous cooling cycles. The biological mechanisms for deep cooling already exist. We can move past the need for expensive, unproven carbon capture machinery by identifying the specific natural processes that ended previous warming periods. This is georeplication. By mimicking the way Earth previously balanced its own atmosphere, we can restore the climate using methods nature has already perfected. When Mount Pinatubo erupted in 1991, it launched 20 million tons of ash and dust into the stratosphere. This event provided a clear demonstration of how the Earth manages atmospheric carbon. In the year following the eruption, global CO2 levels stopped rising. Despite ongoing human activity, the planet achieved a temporary state of net zero emissions because the natural world began pulling carbon down at an accelerated rate. The eruption scattered iron-rich dust into the sea. In areas with downwelling eddies, swirling currents pulling water deep, this iron acted as biological fertilizer. It triggered massive phytoplankton blooms that consumed CO2, died, and sank. These currents pulled the biocarbon into the abyss, safely sequestering it. These natural events are massive. These turquoise swirls, seen here from a satellite off the coast of the British Isles, are phytoplankton blooms large enough to alter the chemistry of the atmosphere. Localized ocean iron fertilization replicates this effect. By adding minute amounts of iron to specific deep-water eddies, we can trigger the same biological carbon scrubbers that Pinatubo activated by accident. Scaling this to just 500 eddies, roughly 1% of the ocean's surface, could remove 60 gigatons of CO2 annually. Because this mimics natural dust storms, the cost remains under $1 per ton, while the resulting blooms provide a massive new food source for collapsing global fisheries. Nature's second removal method is marine calcification. Oysters and shellfish pull calcium and carbon dioxide directly from the water to build hard, protective shells. These shells eventually compact into rock. This organic process has stored 99% of all Earth's carbon, forming geological structures like these white limestone cliffs. We can now produce synthetic limestone aggregate by mimicking the way oysters build their shells. This process combines captured CO2 with waste materials to create a carbon-negative building supply. Every cubic meter of concrete made with this material sequesters half a ton of CO2. As global cities continue to expand, we can transition from quarried rock to synthetic limestone, literally building our future infrastructure out of legacy carbon. Underwater kelp forests are even more efficient than rainforests, pulling down 15% more CO2 per acre than their terrestrial counterparts. When kelp dies in the open ocean, it sinks. Unlike land plants that rot and release their gases, sunken kelp traps its carbon on the seafloor for centuries. Marine permaculture allows us to scale this growth in the open ocean. These seaweed ranches provide raw materials for bioplastics and biofuels, creating a sustainable alternative to petroleum. This creates a double benefit. We can systematically replace fossil fuel feedstocks while simultaneously scrubbing legacy carbon from the atmosphere. Accelerating the transition to renewable energy and stopping active fossil fuel emissions is non-negotiable. We cannot restore the climate while we are still actively polluting it. Adding nature's removal methods to our global network of expensive, energy-intensive machines. Restoration targets the pre-industrial climate that allowed human civilization to flourish. We have the biological tools to reach it. By following the Earth's own methods for carbon removal, we can hand future generations a safe and stable world.